This video will discuss the moons of Jupiter, with most of the time being spent on the four large Galilean satellites. Jupiter is a very interesting system for moons, and if we bring up a little comparison slide just to get us started, the Earth's moon over here, the Earth on the lower right, just to give you a scale of sizes. Mars has 2 satellites. We'll talk about those in a different video. There's asteroids that have satellites. But here we go with the 4 Galilean satellites with Io, Europa, Ganymede, and Callisto. And our moon would fit right in here for its size. So one of the Galilean satellites is a little bit smaller than our moon. The other 3 are a little bit larger. Saturn has a nice set of moons as well. And by the way, this slide does not show all of the moons. So both Jupiter and Saturn have about 60 moons, but many are very small, just captured asteroids. But Saturn has Titan. Uranus has some moderate-sized moons, and then Neptune has Triton. That's a very interesting moon. We'll talk about that in a future video. And Pluto has Charon, although Pluto is not a planet. Another graphic that shows the our moon, the 4 Galilean satellites, and other moons in the solar system. Here we compare the 4 Galilean satellites to the red spot of Jupiter. Back to the Galilean satellites, and again the Earth's moon in here. And then in a row for the order of size. This is not in order of distance from the planet, but we have Io, Europa, Ganymede, and Callisto. These 4 Galilean satellites have, that's their order from Jupiter as I just named them there, they have an interesting sequence of densities. Io has about 3.5 grams per cubic centimeter. Again, water density is 1 gram per cubic centimeter. The second satellite out, Europa, 3 grams per cubic centimeter. The third satellite, Ganymede, 1.9 grams per cubic centimeter. And the last satellite, Callisto, last major satellite, 1.8 grams per cubic centimeter. So we see here that there's a trend in densities similar to the trend in our solar system. The denser objects are close to Jupiter, and presumably Jupiter was warmer in the past. It was never a star, but it emitted more energy in the past than it does now, and it looks like that it had an effect on the type of elements that were retained by these 4 Galilean satellites, with only the heavier elements being retained by Io, and Callisto retaining a good deal of the lighter elements as well. So a little miniature solar system. Another thing that's similar to the solar system is these 4 major satellites of Jupiter orbit in the equator of Jupiter. So they have a kind of an ecliptic plane, like the 8 planets orbit in a plane around the sun. The 4 major satellites of Jupiter orbit in the plane of the equator of Jupiter. They all orbit in the same sense around Jupiter. So here's a photo with Jupiter and the 4 satellites. Galileo, of course, observed these points of light and motion around Jupiter from night to night. He plotted their position, and he realized that these 4 objects were in orbit around Jupiter. So they have the name Galilean satellite in honor of Galileo's observations. Spacecraft have flown by these satellites on numerous occasions, and there was a fairly large surprise, not a surprise to everyone, but a notable set of photographs for the innermost satellite of Jupiter, Io. And this is not a photographic flaw. This is a plume from an active volcano. And every black spot on Io is a volcano. Volcanoes are numerous on this satellite. What's going on here? It's a small object. It should have cooled off from the time it formed. It's very far from the sun, so it's not being molten by sunlight. What is it that would give Io an internal heat source? It's a solid, so we don't talk about it shrinking and releasing gravitational energy. What could cause Io to heat up? Well, let me give you a clue. Its orbit is not circular. Its orbit is not circular. Sometimes it's closer to Jupiter, and another part of its orbit it's further away. Closer and further away. Jupiter, massive planet, lots of gravity. There are huge tidal effects for Io. And by huge, I think the number is several hundred feet that the diameter changes for Io every orbit. And it's a few days orbit, so we have the situation of the stretching back and forth of Io creates friction on the inside. So there's molten material on the inside of Io due to friction heating caused by the tides of Jupiter's gravity on this satellite. When the satellite is close to Jupiter, it gets more elongated. When it goes into its orbit further away from Jupiter, it goes more back to a spherical shape. But stretching back and forth, friction on the inside has created an internal heat source and created molten material. Another view with the plume off to the side here, and these plumes are 150 miles high. The gravity on Io is low, so material can go very far out before it is stopped and comes back by the pull of gravity. So 150 miles high, and again, it almost could be artwork surface, but it's a real surface, is what is actually happening on the surface. And another plume over here, and a large volcano down here. As you look at these slides, these images, what you do not see on the surface are impact craters. All of these are volcanic craters and features left over by the material from the inside of Io coming down, raining down from these plumes. So you don't see impact craters. That tells you that the surface is young. The surface is young. It's been recoated. These volcanoes supply material that covers up impact craters that might occur. So we have a very young surface on Io, and very colorful. The minerals brought out from the interior give Io this colorful nature to its surface. Another example here with, again, the sulfur coating here giving us this bright orangish color. And from a distance, here's a nice view of the plume. So the volcano sending material up here, and then it rains back down in kind of an umbrella or mushroom shape from the surface. And a little animation of the plume in action as the volcano is erupting, sending material upward, and then it comes back down. From 1999 to 2000, a couple of images, and there are other images like this showing changes at the volcanic vent, and especially this one on the right showing the hot material in evidence on the surface of Io. But changes around here, you can see subtle differences and differences in elevation as the eruption occurs. It fills in low spots and continuous recovery. So the satellite here took an image of Io when the sun was on the opposite side of Io from the satellite, from the spacecraft. And in infrared, you can pick up hot spots on the surface of Io. Each of these would be an active volcano. Again, the plume, and again over here with infrared detecting the hot spots, the volcanoes on Io. From the Earth, the Keck Observatory in Hawaii, again above most of the water vapor in our atmosphere, and it can observe in the infrared, and using adaptive optics to correct for the twinkling, the seeing effect in our atmosphere. This telescope can pick up hot spots on Io. Second satellite out, Europa. And again, as you look here, there are very few impact craters. There's a major one here, but few impact craters. Would you think this surface is young or old? And you should say young. The old impact craters have been destroyed, have been recovered. This surface is ice, and this surface is reconstructed, is relayered. So the browns are kind of cracks in the ice. The left one is just the raw photograph, and on the right there's been some photo processing done to sort of refine the details, allow better observations of the cracks in the ice to be noted. These cracks they're not quite cracks like there's ice separating, but there are cracks in the ice. So, and I'll go to this one as well. So, kind of looks almost like a jigsaw puzzle that's attempted to be put together. But there are these striations here where material has come up from the inside and formed kind of a ridge. And you can see that these grooves, these ridges, are on these chunks of ice here. And this is all ice. There's no water visible from the surface. But I would ask, do you think these chunks used to be more one piece? And if so, and they've separated, where would it be easier for ice to move around, if the ice was on land or if the ice was on top of water? And the answer is on top of water. And astronomers think that there may be as much fresh water inside this satellite, underneath the ice, as much fresh water as there is on the Earth. And this water may be in contact with rocky core and minerals, and it's an possible spot where life may exist underneath this ice. Now, there's not going to be much sunlight getting into that water. Does that prevent us from speculating there might be life on Europa underneath the ice coating? No, because life has been found at the bottoms of oceans on the Earth where there's no sunlight, but the life just needs energy, needs some energy. Well, that brings the question, why is there water, liquid water, for this satellite? It's ice on the outside where the energy is radiated to space and it cools down. Why is there water on the inside? Well, again, tidal friction. This moon is not quite as close to the planet Jupiter, but it also has an elliptical orbit like Io, so it gets stretched back and forth, and that supplies energy that would keep the water in a liquid state and not frozen. There's also evidence that water comes out of cracks in the ice. This is ultraviolet data that indicates a water plume outside the poles of Europa. So it's not as thick as what this graphic shows. This is just showing the location and then showing the data. So it's detectable, but it's not thick. It's not like a geyser and not like the volcanic plumes we saw for Io. But there is evidence that there is water coming out from the interior of this moon. And then comparing Europa, Ganymede, and Callisto. Io does not have an ice surface to it. It's coated in minerals from the volcanoes. But these three have ice on the outer part of their crust. So Europa with these ridges, Ganymede, you can see some surface features here, but now we're also seeing impact craters coming up. And then Callisto, the most distant moon, again, impact craters are what we're seeing here, and not volcanoes for either of these. So there's been a little movement of the surface ice for Ganymede, but not much movement of the surface for Callisto. And here the very oldest craters survive in this icy covering. So Ganymede again, and the white spots you see are impact craters. You see some grooves and features of showing a little bit of activity of the ice. And then Callisto, lots of impact craters. All these white areas are impact craters where the rock coming in exposes fresh ice underneath, as opposed to the darker places are old ice on the surface of Callisto that gets weathered by solar radiation, ultraviolet light, and gets a little darker. Jupiter has other moons than just those 4 Galilean satellites. The 4 Galilean satellites, as I've mentioned, orbit in the plane of the equator of Jupiter. But these other satellites really have much different orbits for many of them. There are some more satellites that orbit in the same direction around Jupiter as the Galilean satellites and have nearly circular orbits, and those are called regular satellites when they have a more circular orbit and orbit the planet in the same direction the planet spins. Those would be regular satellites. And then we have irregular satellites that have very elongated elliptical orbits and not in the equatorial plane of the planet, so they're irregular. They don't orbit above the equator of Jupiter. They have tilted orbits, and some go in one direction around Jupiter, some go in the other direction around Jupiter. So we have a hypothesis that some of these, at least, are the result of collisions between small moons of Jupiter. And there are somewhat families of satellites, pieces that orbit in kind of a group around Jupiter. And that would happen if a satellite would split apart. The pieces would tend to follow the same path as the original larger satellite was following before the collision. And then there are captured asteroids. These captured asteroids are very small moons and irregular shaped and in just random type orbits around Jupiter, not in the equatorial plane. Those are the regular satellites. But captured asteroids, some go in one direction around Jupiter, some go in the opposite direction in their motion, their orbits around Jupiter, and then again, very elliptical orbits are common. So why is it that Jupiter has so many moons? As I say, over 60. Why would Jupiter have so many moons? Well, with its large gravity, it's able to capture objects and pull them into an orbit and keep them in orbit and keep them from being lost from the pull of some other object. Jupiter has enough gravity to capture asteroids and keep them in place. So, a quick tour of the major satellites of Jupiter. That was the primary emphasis here. Io, the volcanic satellite with tidal friction giving heating in the core, creating lava, creating pressure that then spews out material out these volcanic vents. Europa, ice covered with ridges and cracks, but probably has water underneath the ice. And then Ganymede and Callisto, the surface is not as refreshed. The surfaces here are old, especially for Callisto. Very old surface, has not been recovered. So keep reading and asking questions, and we'll do more with other satellites in the solar system in a future lecture.